community-based environmental health research in the Arab American community. She's also a postdoctoral fellow at the U.S. Environmental Protection Agency, and she has conducted participant-based air monitoring, land use regression modeling, and linkages to air pollution exposure to biomarkers and health outcomes. For the past 10 years, Dr. Johnson has designed and led studies to assess air pollution exposure and health as a senior researcher in the Air Health Science Division at Health.
So Aaron, just let me know when I'm, in case I miss it, let me know when I'm switched over.
Her research includes development of air pollution models, integrating land use regression, regulatory monitoring, satellite remote sensing, and chemical transport models. Dr. Johnson will be giving an overview of Health Canada's current air pollution exposure research.
All right. All right, can you see my PowerPoint now?
Yeah.
Perfect. All right. Lance, I think we're ready.
Yep, you can hear you're ready.
Great. Okay, so should I go ahead and get started?
Yep. Yeah, you can start anytime. Sorry, yeah, you can start anytime.
Great. Okay, so my name is Marcy Johnson. I'm a research scientist in the exposure assessment section. This is in the same division as the indoor air quality group that Aaron's part of in Canada. And I'm going to be giving more of a broad overview. So I'll be talking about the research, the exposure research that's been done by my section during the past 10 years, obviously highlighting some trends. So first I'll just give a little bit of background. The exposure assessment section is a multidisciplinary research team. We are comprised of about 15 different staff scientists that include engineers, epidemiologists, people with backgrounds in geography, modeling, and statistics. And our mandate is to conduct air pollution exposure research to support the advancement of scientific knowledge and specifically policies to support health protective policy and regulation in Canada. So to do that, we conduct large field studies, household studies, and then we develop and apply cutting-edge tools to refine exposure to health studies, and finally we publish manuscripts in peer-reviewed scientific journals. So we do collaborate fairly extensively with researchers in academic departments, in Health Canada, in other federal departments, as well as local and provincial stakeholders. And I've included some of our common collaborators below. I should mention that in this presentation, I'm going to be talking about some research that I've led and some research that's been led by other members of my group. So I'll be happy to answer any questions about research that I've led, and I'll give it my best shot to research that's been led by other people, but I may wind up referring you to others if you have more detailed technical questions about those studies. And finally, what I'll say is our group conducts exposure research in ambient environment and outdoor air pollution. We do transportation research, and we also do indoor air studies. In this presentation, I'm really going to focus on ambient with a little tiny mention of transportation and indoor at the end. So for our ambient exposure research, most of the goal of this research is mostly driven by the urge to support regulatory action and policy. So most regulatory policies to reduce air pollution are driven by health research. Those studies require detailed information about air pollution exposure in order to accurately estimate the health impact. And then we also do studies that support local and federal decision makers, specifically about how ambient sources may impact ambient air pollution, and providing tools that support regulatory policy and planning. So some of the more specific goals of our ambient exposure research are to characterize the spatial distribution of a number of different priority pollutants, also to identify hotspots and major sources, to improve the coverage of existing data like the national air pollution surveillance data. And so one of the things that we do is we develop what's called land use regression models to predict future urban pollution concentrations. So we also use novel tools to refine exposure models, and we develop hybrid models to predict daily concentrations in non-urban areas and in areas where NAPSs are not available. We evaluate different models for estimating exposure, specifically in health studies. We provide exposure estimates to support health studies, and finally we evaluate regulatory and policy level interventions to reduce ambient concentration. So this schematic kind of shows the evolution of our land use regression modeling research over time. So in the early 2000s, land use regression models were linear regression. They were city-specific, and they focused on a limited number of pollutants, typically nitrogen dioxide, PM2.5, and PM10. Over time, we've expanded those early models. We've looked at novel pollutants, so we've looked at ultrafine, black carbon, PM components. We've looked at novel predictors. So over the years, we've had different types of land use characteristics to see whether they may be associated with ambient pollutants. And as we develop a new sense of what types of predictors may be important, we carry them forward and include them in future models. We have modeled larger geographic regions. We've moved away from just looking at individual cities to trying to look at larger geographic areas. And we've applied different modeling techniques, like geographically, we use regression and machine learning to help us develop more sophisticated models, both for looking at short-term concentrations and long-term concentrations. And then sort of coupled with that, we've developed hybrid models where we combine land use regression with data from map stations and with chemical transport models, or CTM, as well as satellite estimates. And I'll talk a little bit more about what those different approaches can contribute. And then the application of our models is typically the most common area in which we apply them is health studies. So we've linked our land use regression models to mortality, hospitalization, and a variety of long-term health outcomes. We've also incorporated these models in decision-making tools. So we've recently begun to incorporate our land use regression models into integrated urban models, where they can be used to help local planners make decisions about transportation policy and land use. We've also incorporated them into walkability models and to route planners that can help pedestrians and cyclists figure out what route may be least impacted by air pollution based on long-term trends. Okay. So this slide shows our LUR modeling inventory. So I'll just mention, these are the LUR models existing for Canada to which our section has contributed either by leading the study or by providing support, analytical funding, or other types of support, our equipment, field staff, and so forth. So we have about 13 cities that have been covered by LUR models developed or supported by the EAS. A number of different pollutants that we've looked at, the most common are still NO2, PM2.5, the VOCs, especially detected species. And I want to point out too that, like you see, for a lot of these, the data collection periods are the early 2000s or the mid 2000s. And the later models do tend to look at novel outcomes, so looking at some things that are a little bit more exotic than NO2 and particulate matter. And that's an issue that we've discussed internally, is sort of how to go about and whether to go about revisiting this inventory, trying to update those models, and what's the best approach for doing that. So for the next couple slides, I'm just going to give some examples of some novel LUR modeling work that we've done recently. So this slide shows a few models that were led by my colleague, Dr. Scott Reichenthal, in Montreal and Toronto. So on the left, there are two models for UFPs in Montreal and Toronto. On the right-hand side, there are various models for oxidative potential for reactive oxygen species in Toronto. And again, this is a way to try to get at different potential impacts of particulate matter on health. The slide here, led by myself, shows the Calgary Spatial and Temporal Modeling Study. This was a study where we tried to go beyond the boundaries of the city of Calgary and look at some of the bedroom communities around Calgary as well as some of the rural areas. So we did a bit more extensive spatial and temporal modeling to try to get an understanding of how both the spatial gradients varied in urban versus non-urban areas, but also how those concentrations, the temporal trends might have varied in those locations. And there's a list of different pollutants that we've looked at, as well as some of the modeling approaches that we've either applied or that we're in the process of applying. So in addition to land use regression models, there are a number of different approaches that are used to support exposure assessment in Canada. So I put a few on the slide. Satellite remote sensing can provide with estimates of some pollutants. Specifically, particulate matter is what satellite so far does the best job at. There are estimates for some other pollutants, typically particulate matter, fine particulate matter is what does best. Chemical transport models, which can provide a variety of species, and they do provide a temporal trend. So we can have hourly and daily values for chemical transport models like CMAX or GenMax or GeoChem. The limitation is typically that these are quite resource intensive, and so these models provide estimates at a spatial scale that's quite coarse. So we're looking at 10 or 12 kilometers typically. Except maybe there may be a limited focus on an area where we're able to go down to 2 to 4 kilometers with those approaches. The NAP station, I'm sure we're mostly familiar with. Again, provide great hourly and daily values, but at a limited number of locations. So they're not densely located throughout Canada, but they do provide estimates or values for us at about 250 locations. And then, of course, land use regression models. These provide long-term estimates like satellite, and they do provide a very fine scale spatial gradient with the cities, but they don't provide us with any temporal information, so we don't have any hourly or daily values from land use regression. So that brings me to my next slide, which is the hybrid modeling. So hybrid modeling is basically an approach of integrating data from multiple sources so that we can try to leverage the strengths of those different sources, and we can try to mitigate some of the weaknesses. So for example, land use regression models provide us the best sort of spatial resolution, but they don't provide us with any temporal information. So if we combine land use regression models with chemical transport or CPM models, they can help us to provide estimates of daily concentrations or short-term concentrations at a finer spatial scale. So this is a work in progress. In the past, we've often done combinations of NAPS data and LUR models, and that's what sort of led us to explore, well, can we go further? Can we use CPM models, which have a coverage across the entire country rather than just specific urban locations like NAPS? And there, we've looked at a number of different approaches for combining those data. They can be used for full scaling, to provide a scaling factor that can be used directly with a model input. We can predict the model residuals, the difference between a CPM and a NAP or a measured estimate using land use characteristics. There are a number of different ways that these data can be combined, and we're still in the process of exploring all that I think there's this temporal scaling, which is pretty well established. So this next slide shows some examples of daily concentrations based on a GenMax LUR hybrid. These are cherry picked, but we did try to cherry pick them such that we didn't pick all examples that showed good agreement. We tried to pick some that showed good and some that showed bad agreement. What we found for these daily estimates is, unsurprisingly, the daily estimates are not as stable as longer-term estimates, and they do vary by pollutant. So for NO2, we found that they did quite well for daily estimates. So we're seeing R-squared daily for these daily estimates of about 0.5. For PM, we saw a lot of variation, and a lot of that variation was either regional or it was based on the type of PM sampling equipment used at the NAP station. So when we stratified by TOM versus federal method, we saw some differences in the relationship. So I think that we still need to sort of evaluate this in the context of a health study to, I think, really understand, especially for PM, how well these daily estimates relate to the concentrations that we see from measured NAPS data. So after sort of doing some initial test work with hybrid modeling, we expanded to sort of a larger scale project, looking at developing estimates from 2000 to 2014, both daily and annual estimates by combining CMAX with LUR models. So there are a lot of challenges with this. Obviously, CPM models require historically consistent emissions inventories, and so we've been working with Carleton University, and they have been working to rebuild these inventories basically for this 15-year period, and now they've moved even beyond that period. with additional funding from other sources to create these emissions inventories and support CTM modeling in Canada. And so our daily estimates here, again, perform reasonably well. And I'm showing daily NO2, PM2.5, and ozone. I should mention that ozone is just based on the CMAQ model, so that's not actually a hybrid model. That as a regional group is something we haven't really modeled with LUR models, so I show that just for comparison. Okay. So next I'm going to talk a little bit about some of the implications of the application of these different exposure estimates in health studies. Because again, as I sort of started out with, our goal is to really support health studies. So if we're not, able to support them, then I think we need to sort of think about what are the gaps, what data are needed, how can our data be improved to do a better job. So the first thing I want to talk about was led by Dan Krause. This study used 10 LUR models in 10 Canadian cities and linked that with mortality outcomes in the Canadian census cohort, or CanCheck. And basically, the way that Dan calculated this, he looked at it in two different ways. So he looked at the within-city variation based on the LUR model, and then he looked at the between-city variation in NO2 concentrations, and that was based on the average concentration at a citywide level. And what he found was, when compared, the association between NO2 and mortality is driven almost completely by the within-city variation. So again, I showed those hazard ratios below, but that was quite significant, basically suggesting that looking at things at that regional level is not really giving us the information that we need, especially with a very spatially heterogeneous group like NO2. So the next slide is quite on a smaller scale. So this was conducted as part of a study of asthmatic children in Windsor, Ontario. So I think the sample size was about 50. It might have been 100 over the 2 seasons. But basically, we followed these asthmatic kids. We took daily measurements with lung function. Measurements were collected inside and outside their homes. The outside measurements were used as part of the development of the land use regression model. So these land use regression models, we scaled them using MAP data. So we scaled them up or down based on the daily concentration at the nearest MAP station. And then what we did was we looked at the measurement of the home, we looked at the measurement of the MAP station, and we looked at that scaled measurement, the ambient model of the home. And we looked at the relationship between those different measures and the daily lung function measured in the children. And what we saw was, it's not a perfect relationship, but overall, the measurements at the home were more consistent with the ambient model measurements. And so what we saw is that the associations or the effect estimates for NO2 at these homes was more consistent between those scaled estimates than it was for the MAP. So the MAP, as you can see, you're sort of biased towards the null and less likely to be able to see an association. And then again, just in the interest of fairness, we showed the results for FEV1 and PEF. So you can see that, you're not always going to see a significant association, but overall the trends seem to carry that we saw a more consistent association, more consistent associations looking at the modeled estimates and the measured estimates compared with the MAP. So the next couple slides, I'm showing another application of daily estimated concentrations. In this study, we estimated daily concentrations for the birth cohort MIREC, which was conducted in multiple Canadian cities. And our goal here was to identify whether there were critical windows when exposure was more likely to lead to lower birth weight. So basically what we did was we did an iterative Bayesian modeling approach to randomly select date periods during the pregnancy. And for those date periods, we looked to see whether the exposure during those randomly selected periods was associated with lower birth weight. And then we did what we called a selection density. So we compiled the number of times each day showed up as being significantly associated with the adverse birth outcome. And that was sort of compiled against that pregnancy day. So what you can see is that for PM2.5, we did see there were different time periods that were more significantly associated when exposure to PM2.5 was more significantly associated with lower birth weight. For NO2, there's less difference in the timing of exposure. Now, I don't want this to be misleading. When we look at NO2 and as it relates to adverse birth outcomes in the same population, we did see a strong association between long-term concentration. But what we didn't see was a strong variation in the timing of exposure, as we did for PM2.5. And then just plotting that out sort of on a calendar of pregnancy, what we see is that the sort of critical period, both for NO2 and PM2.5, we see sort of a critical period at the end of the third trimester, which we hypothesize may be associated with triggering, not clinically, but early birth, early delivery, which may result in a lower than expected birth weight. And then we also see periods of time in earlier pregnancy, which I just want you to notice are not directly overlapping with the trimesters. So if we look at trimester 1, trimester 2, and trimester 3 exposure, we might underestimate or miss some of these associations. So this is another example of the application of daily estimates. So some final implications. So we've also looked at associations between short-term exposure to air pollution and hospitalization, and we found that for some outcomes like heart attack, the association was stronger in neighborhoods with high long-term NO2 based on our LUR model estimates. This was done in the city of Calgary, and it's publication now. We also found that we saw significant associations in non-urban areas. So when we stratified our CCHS population of a few hundred thousand, and we looked at just, I think, the 80,000 who lived outside of a catchment area, we saw quite significant associations in some cases between the exposure to NO2 and to PM2.5 with a number of different respiratory outcomes. So switching course again, I'll talk for the next few slides about source characterization. So, of course, our modeling approaches do to some extent capture sources in the sense that our model can tell us which sources are important predictors, but they don't necessarily explicitly tell us what that contribution of those different sources is. So, for example, for LUR models, the model may tell us what sources explain variation in the pollutant concentration. But they don't tell us the overall contribution of that source. So some of the different ways that we can look at source contributions are discussed a little bit in the next few slides. So one way is, of course, using different approaches through chemical transport models. The example I've given here is some work that's being done for us by Carleton University, by Dr. Amir Hakami. I know that similar work is possible and is being done by Environment and Climate Change Canada using GenMax. The exact approach is different, but the results are, I don't want to say comparable, but we certainly can get different estimates of source characterization from different chemical transport models. The other approach that we can use, and one that is maybe a bit more familiar, is using statistical, so PCA or PMF, or chemical mass balance models. These approaches, instead of modeling the source contribution, basically, I guess, are receptor-based. So we collect a bunch of measurements in the field, and then we use those measurements, typically of PM components for different pollutant species, to help us try to understand the relative contribution by looking at either source indicators, individual species or source indicators, or mixtures that are indicative of a specific source. So the results that I've shown here were developed by Dr. Angelos Anastassopoulos. These represent some results, some initial statistical source apportionment work that he did in the city of Calgary to support our CSTEM study. So this is based on the NAPS data, and I know that he's expanding this to look at some of the field data that were collected as well. But again, this can give us a rough idea of the contribution of some of the different sources that contribute to ambient pollution in the area. And the goal of this type of analysis is to then link those sources, both to understand those sources so they can be perhaps better controlled, but also potentially to link those sources back to health studies. So the next two slides are for a study called KMAP, which I'm sure most of you are quite familiar with, maybe more than I am, so I'll try not to fumble through it too much. Again, this was led by Dr. Anastassopoulos. Here, the goal is not to link back to health, but rather to use source apportionment, to use source characterization to help to try to understand whether regulatory policies have the protective effect that was expected. So in this case, it was looking at a reduction, a regulation to reduce the sulfur content of marine fuel. And in this case, the challenge in knowing whether that is effective is that, you know, you could see a reduction in ambient pollution concentrations because you had a factory closed down at the same time. Coincidentally, you could fail to see a reduction in ambient pollution because you had a source introduced at the same time that the marine regulation went into effect. So the goal here is to use source characterization to have a more refined answer to that question of whether the regulation was effective. So here you can kind of see buried behind these pictures of the port and I guess the cruise ship. You can see some pictures of the sampling sites in and around Halifax. The next slide shows some of the results from the study, basically a timeline of concentrations against sort of the phases of the fuel regulation. And we can see that ambient concentrations decrease, but in addition to that, sort of an analysis of the PM composition shows that there was a decrease in some of the PM components like nickel and vanadium, sulfur and sulfate, which reflect that fuel switch. So we expected, you know, based on that regulatory change. And then, of course, this was corroborated by analysis of the sites that were up and down in the report. So, again, changing gears a little bit, I'm going to talk in the next couple slides about some of the knowledge translation or some of the use of our data to support, I guess, communications and decision making using air pollution exposure data and expertise. So integrated urban models basically stimulate land use and transportation systems, and specifically the feedback and interactions between those systems. So when we're contemplating changes in an urban area, these can allow decision makers to evaluate potential impacts of different urban growth scenarios in transportation infrastructures and policies. And so these models have been around since the 1960s. In the beginning, they really focused on traffic, and I think really the goal is to reduce traffic congestion, which is still a wonderful goal. But the models have expanded so that they really take into account a number of social, economic, and health indicators. And our goal is to expand them even further to look at environmental, specifically air pollution exposure and health indicators. So our goal here was to develop a user-friendly tool, something that's freely available and that can allow policymakers, local decision makers, and stakeholders to sort of input scenarios of interest in their areas, their urban areas, and see what those potential results might be on some of the indicators that we programmed in. So this is work that is that's being done by Health Canada in collaboration with the University of Windsor and Ryerson University, and specifically with Dr. Hannah Mao and Dr. Tibor Liano. This next slide shows sort of a graphic of the Smart Plans IUM. So you can see it's an integrated urban model because it integrates a number of different very sophisticated models with a land use module, transportation, sustainability, there's a population model in there somewhere. And what we've really added to this is we've added to the sustainability indicators module and the health benefits module. And you can see on the right-hand side some of the specific indicators that we've looked at. And on the bottom of the slide, some examples of some of the scenarios that we've looked at so far. So in Halifax and London, we looked at rapid transit corridors. In Vancouver, we looked at the expansion of the transit network and distance-based road pricing. And then we're working on Ottawa right now, and the final city we'll look at under this study is Calgary next year. So moving on, we also provide our data in a very different way through the Canadian Urban Environmental Health Research Consortium, better known as CANUE. CANUE acts as a web platform that provides access to exposure data across different media. So we provide air pollution data, as does Environment and Climate Change Canada and some academic partners. But the CANUE consortium also holds green space data, noise data, weather data, and a variety of other types of information that are linkable to place so that we can examine the impacts of things like air pollution in conjunction with other potential risk factors or mitigating factors. And so what Canoe does is they take all of our data, they link it to postal codes and make it readily available to health researchers and other stakeholders who are interested in analyzing this data. So if anyone hasn't looked at the Canoe website, I would strongly encourage you to look at it. Just know that there's a stream backlog. So they have a lot of data in their